Welcome to Chapter 8, Section 3, called Test for Parallelograms. This is for Integrated Math 2, or IM2. So a couple things you'll see on your screen here. Just before we get started, the first thing you should see is a due date. I don't see that on my teacher preview here, but you will see it on your student side. The second thing is the number of attempts. Remember, you always have unlimited attempts on homework, tests, and quizzes. Number of questions just lets you know how many are on this particular assignment. Grading policy is always best score, so whichever attempt is the best one is one you get to keep. Partial credit is enabled, so if you answer one of 4 questions correctly, you get credit for 1 question, or however many you answered correctly. Down here it says, please remember once you start your homework, you must finish it before you can work on anything else. What that means is once I click the start button down here, down here in the bottom right corner, you will see a submit assignment button. That is how you finish your assignment. By clicking that button. So as soon as I want to leave the screen, I don't want to click the little X to close the tab or just close the computer down. I want to actually click the submit assignment button because it does 2 main things. Number 1, like it said on that last screen, you can't work on anything else. That means that Alex is going to freeze all of your other assignments and resources. It's assuming you want to leave this attempt open. That's what it's trying to do for you anyway. Remember, you have unlimited attempts. You don't need to leave it open. So just click submit assignment button and you won't have any of those lockout issues. It saves your place as well. So if you've already answered some of these questions, it will know that and it will start you back up in that same place. So don't worry about, having to restart. The second big thing it does is it affects the grade book. So your teacher can actually see what you've been working on. Until you click submit assignment, your account's basically frozen in that place or on that, assignment. So just good habit to get into. Always, always, always click the submit assignment button down here in the bottom right corner. These 3 pieces on the side here, we have explanation. It tells you you're going to lose your current question attempt because it's going to give you the answer to this question. So it's not going to give you the answer unless you type it in, but it's a very neat resource. You get to kind of see how this problem in particular is worked out. Example, we'll show you an example very similar to what you're looking at. Not quite the same, a little bit different coordinates on this one, but it shows you what to do. It shows you how to find the midpoint here, gives you the midpoint formula. That's definitely very important. So once you go through and you understand what it wants you to do and how to do it, you can close this. You can open up another one if you want to see another example, or you can message your teacher directly from the screen. It attaches a picture so we know where to come help you. All right, midpoint formula. Midpoint. What we do is we write it as a coordinate like this, comma in between. And what we're going to do is for the x coordinate, we're going to have x1 plus x2. So the x coordinate of point 1 plus the x coordinate of point 2, and we're going to divide that by 2. Because remember, midpoint is halfway. Oh my goodness. And then we're going to go y1, it's doing x again, y1 plus y2, and again, divide by 2. So we're adding the terms this time instead of subtracting them, and then we're going to divide by 2. So this is the midpoint formula, and again, we're going to be given 2 points. So in this case, we're given P, I don't know where I'm writing equals, but they wrote equals up there. I think that's why I did that. Sometimes they put the equal sign and sometimes they don't. It's kind of interesting. So this is x1, y1, this is x2, y2. Now I keep doing this in this order where I'm doing point 1, then point 2. Does that really matter? Could I do it the other way? Could I say that this is point 2 and this is point 1? Yes, I can. The main thing is once I decide which one is point 1 and which one is point 2, I have to keep that consistent for the entire problem. So I can't say, to find my x's, that this is point 2 and this is point 1, and then when I go to my y's, I flip it and go point 1 and point 2. That's going to change some of my signs and change things a little bit. Because we're adding, it's not going to make as big a deal on this one. When we're subtracting with the distance formula, that makes a very big deal because that might change that double negative problem where it changes it to a positive. So just be careful about that, but you can choose this is point 2 and this is point 1. That's perfectly fine if that's what you wanted to do. And if I was looking at this, that actually might be how I do it on the graph. I tend to go from left to right for whatever reason when I'm looking at this. So I'd say Q is point 1 and P is point 2. But again, doesn't matter which one is which as long as you choose and you keep it that way. All right, so let's go ahead and change this up a little bit. So we're going to have our coordinates here. It's going to be plus, and then we're dividing by 2 no matter what. So these pieces aren't going to change. What is going to change is what we plug in here. So x1, I changed my mind on that one. This one's x1, -5, and this one's x2, so -1. And then y1 is 8, and y2 is -6. So now we just want to reduce. So I have -5 minus 1. Well, that's -6. I had 5 negative, I want one more negative. And then over here I have 8 plus -6. So it's really 8 minus 6. So I have 2, sorry, not 4. 2 over 2. All right, I'm going to reduce one more time because these are both even, so I can reduce these. -6 divided by 2 is -3, and 2 divided by 2 is 1. So my midpoint is going to be this coordinate, -3, 1. -3, 1. And they tend to label the midpoint M, just because it kind of makes it very easy to think about there. Okay, so for this one, we need to kind of take a step back. In the last couple sections, we've been learning about parallelograms. And there's definitely some important pieces in parallelograms. When we start with a parallelogram, so if I can draw, oh, that's a really horrible parallelogram over there. I don't think, no, they don't give me the option to do parallelogram over there. So I'll just try my best. We're going to pretend like that's a very nicely drawn parallelogram. So if I start with a parallelogram, then I know opposite sides are parallel. That's the basic definition of a parallelogram. I know opposite sides are congruent. That's one of the first properties. Opposite angles are congruent. So going across like this, opposite sides of the parallelogram. So opposite angles and opposite sides are congruent. The diagonals, if I draw the diagonals like this, they bisect each other. Doesn't mean that the diagonals are equal to each other. That's in a very special parallelogram, but they always cut each other in half, which means this is just basically the midpoint of both. That's another way of saying that. Consecutive angles, so one angle right after the other, like this, one and then the next one, add up to 180 degrees, or are called supplementary angles. I can do that across the side, I can do that across the bottom, I can do it across the top, as long as it's one right after the other. So let's see, that's 1, 2, I'm trying to think, did I miss one? Opposite sides, opposite angles, diagonals, supplementary. Which one did I miss there? The opposite sides are parallel as part of the definition, so that's not the one I was looking for. Let's see. Oh, the other one they gave us was the alternate interior angles are congruent. And that's because if I draw the diagonals, that's considered a transversal going through two parallel lines. So now I can go angle on one side of the transversal, go to the opposite side and slide all the way down. That's an alternate interior angle, so those are congruent. And then I can do the same thing on this side, go to the opposite side on the top there. So these are the properties that are given to us if we know that it's a parallelogram, if we're given that it's a parallelogram. But if we're being asked to prove that it's a parallelogram, so we know it's a quadrilateral because it's 4 sides, and they want us to know, based on the markings, can we prove that it's a parallelogram? So we can actually use a lot of these same ideas to prove that it's a parallelogram. And again, if you have your notes page, which I highly recommend you should have your notes page in front of you, there's a very nice little graphic that helps, put all these together. So the first one that we have is just to show the definition, right? If we can see that the opposite sides are parallel, and I don't mean see as in, oh, it looks like they're parallel. I mean, we actually see the parallel marks, like these parallel marks. So if they show us this, then that's a parallelogram. The second part is opposite sides are congruent. So that was one of the ones, I know I marked all this up crazy up here, but opposite sides are congruent. If we can show this, both pairs of opposite sides are congruent, it's a parallelogram. If we can do the same thing with the angles, like this. If I can show that opposite angles are congruent, that is a parallelogram. Then we have also the diagonal. This is actually the 5th one on the diagram if you're looking at the diagram with me here. And I know I don't have it up on the screen, but again, it's on your notes page. So the fifth one is talking about the diagonals bisecting each other, which is one of the properties we just talked about. The diagonals always bisect each other in a parallelogram. So these four come directly from this same idea. They're just kind of the opposite. This is, if I have a parallelogram, these things are true. Well, if these things are true, then I have a parallelogram. So I can go back and forth with that. The only one that's not on here, give me some messages up here, is this number 4, if you're looking at that notes diagram. And it's if one side is congruent and parallel. If you see these markings, then it's also a parallelogram. And there's a very specific reason for that, just because we can go through and we can show opposite or alternate interior angles are congruent. I can show that this is congruent to itself by reflex. So I would have side, angle, side. With triangle 1 and triangle 2, I could prove that they were congruent to each other. Once I prove they're congruent to each other, then I can go through and use corresponding sides of congruent triangles are congruent. And I can show that the opposite sides would be congruent on here. Or I can show opposite angles are congruent because they're corresponding. So once I have some of these pieces put together, I can start to prove the rest of the parallelogram pieces by just having the sides congruent and parallel. So it has to be the same side. It can't be, I can't have it like this and have one side congruent and one side parallel. It has to be the same side is congruent and parallel. And then we can go, yep, that is a parallelogram. So really what we're going to do is we're going to go through and look for one of these 5 properties and just match it up. So in here, I can see opposite sides are parallel. So this is a parallelogram. On this one, I have parallel, parallel, and then I have this angle here and this angle here. This is an alternate interior angle. It's going from transversal to parallel to parallel. So these are alternate interior angles. I could show that this middle one is congruent to itself as far as like using reflex, but because I don't have any other pieces, I'd only have an angle and a side. I don't have anything else. There's nothing else I could prove with this. So this is not necessarily a parallelogram. I need a little bit more information to continue on this one. This guy is showing me that the diagonals are bisecting. So this is a parallelogram. That's true. That's this guy down here. And then we have alternate interior angles are congruent. So with this one I can go transversal to parallel, transversal to parallel. So using alternate interior angles, if alternate interior angles are congruent, then the lines are parallel. So I could use these one arcs to show that AB is parallel to CD. And then the 2 arcs, that goes from the same transversal but a different parallel. So it goes to the sides. So I can show that both sides are parallel, or opposite sides are parallel. Both pairs of sides, opposite sides are parallel, using alternate interior angles. So they're being a little tricky with that one, but that is one of the ones they want you to remember. Definitely, we use that quite a bit from when we were doing parallel lines. All right, let's go ahead and check that guy. We are good to go. Okay. So we're going to do isosceles triangle. EFG is shown. Give the coordinates of F. And so with this one, I know on the notes diagram, when I did this in class, it was actually more diamond looking. So, you know, just adding another triangle down here. But as long as we're kind of thinking through, they do give us some pieces here. So I'm going to go ahead. You know what? No. I'm going to save it real quick just in case I need to bring that back. And I'm going to give myself a new one because we don't need this one up here right now. But I didn't want to completely erase it because then I'd have to redraw that if we need it later. So I'm going to go like this just so that I can draw this. So I have 0 and R. This is my coordinate up here. I have negative Q and 0. So even though it's Q and R, well, what they want us to do is fill this piece in here. So we need to think about a couple properties for an equilateral or an isosceles triangle, not equilateral, but isosceles. So isosceles means that these are the same length, right? They already show us that. These are the same exact length. If we have an isosceles triangle, though, it's the same length. If I go straight down, which is actually the axes here, it's going to be perpendicular to the bottom, and it's going to cut it in half. So I know that this length is going to be equal to this length on this side. And that's just one of those properties of an equilateral triangle. It has to do with the perpendicular bisector. So I know it's perpendicular, and because it's equidistant from the endpoints here, they're the same distance, I know it's a perpendicular bisector, meaning it's going to cut that line in half on the bottom. So I'm kind of combining a couple of things there as far as definitions. And definitely when we're in the geometry sections here, it's very important to kind of study and make sure that you're paying attention to all these different definitions and postulates and theorems and all these things that come up, because we reuse them constantly. So the more you study them, the easier this becomes, just because it's easier to recall the more we look at them. All right, so if I know that this cuts it in half, and this is my 0, 0 mark, by the way, this is the origin of the graph. Well, if I'm going left negative q, so that's what negative q means, I went left q. I don't know what q is, but it stands for a number. So if I went q units to the left, I'm going to go q units to the right, but it's going to be positive, right? Because it's positive, it's right. It's negative because it's left. So I'm just going to have q here. So I've already filled in part of my coordinate for f. Now I need to know what is my y coordinate. Well, I'm on the x-axis, aren't I? So the x-axis, if it's on the x-axis, I'm not going up or down at all. It's just going to be 0. So it's just a matter of kind of looking at it. What do I know about this shape? And how can I use my knowledge of this shape and other properties of, lines and isosceles triangles and things like that? How can I use these properties to get what I need to solve this problem? And I know we do something very, very similar when we were doing the rhombus, which is the diamond type shape. We actually had 2 coordinates to fill in on that one. So we filled in the coordinate just like we did here, and then we also filled in another coordinate at the bottom. So it's just another one of those, filling in pieces. If we were to do that here, now we would be on the y-axis down here if we were to fill in a diamond. So we would still have 0 for x because we didn't go right or left. And we would use that same idea. If I went q this way, I'd go q this way. Well, if I went r up, I'd go r down. Because a rhombus, especially if they tell you that it's a rhombus, which they did on this one, they told me it was an isosceles triangle on this one. By this one, sorry, for the first one, I meant the notes page. On a rhombus, that means that all sides are congruent, which we can think of the very basic rhombus of a square. That's the idea. But rhombuses can be more squished and look more like a diamond. All right. So let's go ahead and keep going here. Okay, so this one, we have a couple of pieces that we have to remember how to work here. And they're actually kind of telling us down here what we're going to be using. So it says, consider this parallelogram, JKLM. And note that JKLM has these vertices, so it gives us the vertices. And compute the following to determine if JKLM is a parallelogram. So remember, in order for it to be a parallelogram, and that's why I'm happy I saved that other one. Let's go back. Boom. So in order to prove this a parallelogram, I need to show at least one of these properties. So if I'm looking at this one, it says find the length of KL and the length of JM. So it's having me find the length of KL, which is the side, and the length of JM, which is the other side here, so kind of the left and the right side. And then it's saying find the length of LM and the length of JK. So LM is the bottom and JK is the top. So we're focusing on this guy here. This is the one that we're focusing on. We're going to try to prove that opposite sides are congruent. So in order to do that, we're going to need the distance formula, because these are all kind of diagonal lines, right? None of them are straight across, left and right. None of them are straight up and down, or horizontal and vertical. So that means that we're going to have to use the distance formula. So the distance formula is, whoops, that came out really sloppy. What happened there? Turned my board sideways. This, so we have x2 minus x1 squared. So we're subtracting the x coordinates from each other. And then we're going to add the difference of the y coordinates. Also, difference meaning subtracted, and we're going to square that. This comes directly from Pythagorean theorem. I think we've gone through and done some of those explorations before, but this is the idea of using a triangle. So if I were to, draw a right triangle here with this one, like bring this line straight down and over, the difference of the y's would be here, the difference of the x's would be right here, and then a squared plus b squared equals c squared. Here's a squared, here's b squared, and then this would be c squared, but if you notice I'm taking the square root of the other side, so instead of saying c squared, I just took the square root. That's quite literally where the distance formula comes from, is Pythagorean theorem. All right, so now that I've gotten off track a little bit, let's go ahead and do this. So we have KL, and I'm going to write, so I have 1, 2 for K, and L, just that way I don't get mixed up here trying to look back and forth. All right, so I have, remember that goes X, Y, X, Y. And labeling it for yourself just makes it a little bit easier, so you don't have to worry, about which X, which Y. And I even go a little further and go like this. So it's X2, X1, Y2, not comma, why did I put a comma? Minus 2 squared. So now I have -2 squared, because we combine, -7 squared, and I get 4. -2 squared is 4, plus -7 squared is 49. So I would end up with 49 plus 4, which is 53. And I'm going to leave it under the square root sign because that's I'm not going to be able to simplify that at all. And they don't want decimals. It says not decimal approximations. So you'd only change that if, for some reason, you could pull like a square out of it. But you're not going to actually type it into a calculator. All right, so let's do JM. So J is -2, 3. M is -4, -4. All right, so we're going to have, and then it goes XY, XY again, so -4 minus -2. Make sure you do the minus negative. This minus is part of the formula. So that doesn't take the place of this one. They're both there. And we need to make sure we put them both there because it's actually going to change to a plus sign here when we go to simplify this. So -4 minus 3. So then negative minus, that turns into a plus. So I have -4 plus 2. Well, that's -2 plus, and then I have -7. Ooh, look at that. We ended up with the same numbers, -2 and -7. So we're going to end up with 53 again. I don't necessarily need to work out each little piece here again. I know it's going to work out exactly the same way as the last one did. I'm going to be a little bit lazy here and go copy, paste. All right. So these ones, most likely, it's not that they can't be the same length, but we can pretty much see they're not going to be the same length. These two are going to be shorter. Don't always trust the diagram, but when it's on a coordinate grid, we can trust it a little bit more on that one. All right, I'm going to erase some of this just so I have more room. And I'm going to have LM. So L was -1, -5, and M was -4, -4. All right, so we're going to have -4 minus -1 plus -4 minus -5. So now this is going to turn into a plus, this is going to turn into a plus, and we have -3 squared plus 1 squared. So just simplifying there. And then I get 9 plus 1, which is 10. Okay. Oopsie, why did it do that? Okay, so now we're going to do the same thing, but we're going to do JK. So let's see, JK. So J is -2, 3, and K is 1, 2. So I'm going to have 1, minus negative 2 plus 2 minus 3. So I'm going to end up with 3 squared plus 1 negative 1 squared. Well, when we square it, just because they're backwards, it's not going to make any difference, because if you notice this became positive, same thing. This will become, it'll be 9 and it'll be 1 again. So it's the same thing. So we ended up with the same thing. So we just proved that opposite sides are congruent. So we just want to go down here and choose that. So the quadrilateral is not a parallelogram. Well, we just proved it is. So the quadrilateral is a parallelogram because one pair of opposite sides that are congruent, even though the other sides are not congruent. Well, that's not true. One pair has to be congruent. Both pairs have to be congruent. Is a parallelogram because it has two pairs of opposite sides that are congruent, and it cannot be determined if the quadrilateral is a parallelogram. So that would be, if it didn't fit, if we weren't using one of the rules, which with this one, they're going to be using one of the rules. We're either going to be testing lengths, or we're going to be doing something with a transversal on this one. I think a lot of them have the idea of length. The one that we did on the notes page also messes a little bit with slope to prove that one pair of sides is both congruent and parallel. So we could also do that. If you proved that JM and KL were congruent, which we did, and then we could also look at the slope of JM and KL. If they were the same slope, which they are, then that would also be that was one of the special rules for proving a parallelogram. So that's what they had us do on the notes page. All right, so that was section 3. I will see you in section 4.